Hey, good morning there, Etechians. I am off to Sacramento, so I thought I would make this little video for you so you can do your electrical power problems. And so let's review a little first before we get started on electrical power. First, let's review what power is, and then we'll review Ohm's law. And then we will get into electrical power itself. So electrical power. So these are what we'll do. So to review, let's begin with our definition of power. Now remember that power is the rate at which energy, and sometimes it's work, it's the rate at which you do energy, a time rate, the amount of energy you use per unit time. And so sometimes we'll say that the power is equal to, we'll say capital E for energy over time, or sometimes we'll do it in terms of work. And I think that's mainly what we did, is we said power is equal to work over time. In fact, we'll go ahead and use this definition or this variable work and just say that it's equivalent to energy. So so we want to relate this to electricity. I mean, obviously, if you have a circuit where you have current flowing in a light bulb or something and it's giving off light, it's using energy at a certain rate. And some motors or some electrical applications use energy very, very fast, and some, just if you have like a digital watch or something like that, it will use the energy very, 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 very slowly, so the battery will last a long time. So it all depends on the application. So let's review Ohm's law. In Ohm's law, we said that I'll start off with resistance. That the resistance of a circuit is defined to be the voltage that's required to make an amp or to make a certain amount of current flow through it. It's a voltage over current. And we said that resistance, this is resistance here, resistance equals voltage over current. And we made that an equation where R equals V over I. And remember that what voltage is how much energy is in a certain quantity of charge flowing through a wire or moving through a motor or whatever. So that's energy contained, it's energy per unit charge, which is a joule of energy per coulomb of charge, which we called a volt, which we abbreviate with a capital V. And then we said, remember, the current is the amount of charge flowing. It's the coulombs of charge. It's the charge per unit time. Let's state it quantities, and then I'll go to units. So charge per unit time, and of course our units for charge, we use our coulombs per second. Coulombs per second, and then we said that a coulomb per second is an amp, which we abbreviate with an A. Okay. Now let's take a look at power. We said power, work over time. Oh, let's go through the units with that. That's joules per second, right? And a joule per second is a watt. Well, look what we got here. We got joules per second, or watts over here. And look at voltage. Voltage is a joule per coulomb, but current is a coulomb per second. Okay, now that's the key to understanding how we get power from Ohm's law. So let's do that. If we take a look at current, current is, the way we measure current, or an ampere, is a coulomb per second, the amount of charge per unit time is current, and voltage is equal to the amount of energy measured in joules are contained in a certain quantity of charge, joules per coulomb. Well, what would happen if I multiplied these two together? What if I said current times voltage? What if I did that? Well, current is, as we said, is a coulomb per second times voltage, which is a joule per coulomb. What happens? Well, the coulombs cancel out. A coulomb per second times a joule per coulomb, you get a joule per second. And what is a joule per second? That's a watt. Measure of power. So, just by looking at the units involved, we can now conclude that electrical power is equal to current times voltage. P equals, P equals I times V. PIV. Well, power equals current times voltage. So if you have an electrical circuit that's pumping out energy, that's pumping out energy at a certain rate, well, if we measure the current, how much current is flowing, and then we measure the voltage drop across that circuit element, then we can calculate the power in watts. So I've got some problems that you're going to be solving. I'd like your substitute teacher now to hand those problems out and get to work on them. Let's do an example of the kind of problem you're going to do real quick. So let's just do an example. A resistor has 20 ohms and has 2 amps of current flowing through it. Find the voltage drop across the resistor and the power of the resistor. So let's work this problem. And I would like you to use the given, find, solve format. So given. So we've got some resistor here, and this zigzaggy thing is the symbol we use for a resistor. And we're going to say that R is equal to 20 ohms, and that I is equal to 2 amps. Find the voltage across the resistor and the power of the resistor. So this is how you would set it up with give and find, when you're setting up a problem like this. Now let's solve it. Well, what do we know about voltage? Well, we know that Ohm's law is resistance is equal to voltage over current. So that I can solve for voltage. V equals IR. You can use this as your basic equation. Ohm's law is usually expressed like this, by the way. And so we've got 2 amps. And the resistor is 20 ohms. But I always like to think of an ohm as a volt per amp. How much voltage I need to get 1 amp to flow through the resistor. So in this case, we need 20 volts to get 1 amp to flow through it. That's the resistance of this device. And so I can say, oh, well, 2 times 20 is 40. Amps cancels amps, 40 volts. And that's my answer. And then to find power, well, power equals the current times the voltage. So power is equal to the current, which is given to be 2 amps. And we calculated 40 volts. So the power is 2 times 40 is 80 watts. Okay, remember that this is, an amp is a coulomb per second, and a volt is a joule per coulomb. Joules per second is a watt. So, oops. So all that was on. There we go. So there's how I want. This is how I want you to set up all 6 of the problems on the homework, or not on the homework, on the classwork, because I'd like you to do it right now, and I'd like you to have it done before the end of the period. So good luck, and I will see you tomorrow, and I'll expect all of these problems to be done. We'll whiteboard them, grade them, and so on. Thank you. That is all.